Welcome, everyone. Thank you for joining us for today's VFS Technical Talk as Bell reveals the revolutionary electrically distributed anti-torque demonstrator. I'm Jim Sherman. I'm the Director of Strategic Development here at the Vertical Flight Society. For today's program, we have Eric Sinusas, a Program Director at Bell, to give our little talk. So before we get started, I have a little housekeeping. We will be taking questions after the presentation. So as you come up with your questions during the presentation, please enter them into the chat or question box in your GoToWebinar chat panel. Please note that this broadcast will be recorded and posted on the VFS YouTube site, as well as linked through the VFS homepage. So with that, I'm going to go ahead and kick us off. So our speaker today is Eric Sinusas. He oversees Bell's EDAT, or Electrically Distributed Anti-Torque Innovation, as the Program Director. This includes the Bell 505, Bell 407, and Bell 429 programs as part of his responsibility, and he's responsible for teams in Mirabel and Fort Worth. During his career at Bell, he has served in several roles across the business, notably his role as manager of drive systems, where he is responsible for assuring the technical integrity of drive systems for all programs and ensuring a deep pipeline of drive systems design and analysis talent. Eric has 9 published patents to date and has been the recipient of the AHS, now VFS, Francois-Xavier Bagnoud Award, recognizing his contribution to vertical flight technology. Eric holds a Bachelor of Science in Mechanical Engineering from Lehigh University and a Master's in Business Administration from Southern Methodist University. And with that, Eric, I will turn it over to you.
Okay, thank you, Jim, for the introduction. Maybe, Jim, if you can just confirm you can hear me okay?
Can hear you loud and clear, yes, sir.
Perfect, thank you. Well, it is my distinct honor to have this opportunity today, so thank you all for joining. I'm a longtime member of AHS, now VFS, attending the forums, and you know, I will say the one nice thing about this format here, that COVID is forcing us into, is we can have a whole room full of folks virtually attending this. As someone from experience, I know that some of these presentation rooms in the convention halls can get kind of standing room only at times, so this is nice. We can all sit in our comfort of our own locations and dial in and listen. So very happy for this opportunity. So I'm just going to come out and tell everybody I have one slide and you're looking at it. So I think a lot of this is going to be about dialogue, discussion, and questions. I really do want to make sure that I address questions out there. This is obviously visually unique. Mechanically and electrically, it's also even more unique. And I'll get into some of those details, and I'm really excited to see what kind of questions we have and hopefully have a really good dialogue. So without further ado, let me start by describing what EDAT is. So obviously the acronym electrically distributed anti-torque, you can see visually what that means. We have 4 distributed electric motors on off of the tail boom, and they are driving what we're referring to as fans as opposed to rotors. And the main reason that we're calling them fans instead of rotors is that they're not your typical anti-torque system where you have either an open tail rotor or a closed tail rotor. These are in fact fans, and the reason is that they have fixed pitch blades. So there is no pitch change mechanism, there's no control tubes, there's no actuators dynamically changing the pitch of the blades in order to modulate thrust as a typical rotor system, either the tail rotor or main rotor has today. So these are, again, fixed pitch blades, and thrust is controlled with varying the RPM of the motors. So that's one of the nice benefits of electric propulsion, is that motor RPM is a very easy dial to tune. So at a very high level, we have the pilot's feet and the pedals are linked to a electronic signal that goes through a motor controller and a whole electrical control system. And ultimately, the pilot's pedal position translates into an RPM command to the motors. And in fact, just for note, the fans will actually go across zero. So these fans will actually rotate in the positive direction up to roughly, I don't want to get quoted on this, but roughly 7,000 RPM is the max RPM we have these fans going to. And that's in the positive direction and the negative direction. So they actually are crossing zero and spinning in both directions in order to give the pilot all the controllability that he or she needs. At a high level, again, maybe just describing the system, what I'm going to do is really talk through what is the system so we all understand what it is. And then I would like to, after I do that, I'd like to play a video so we can all see it. And then I'm going to get into some of the specific benefits and then really open it up for questions. And please, I believe what we're going to do for questions is you can type them to Jim and then he's going to read them off. So by all means, start piling in the questions as we go. So again, I've already described that we have 4 electric motors in the back with fixed pitch fan blades. So very simple mechanism. There's no moving parts back there other than the shaft on the motor and a couple of bearings that houses. We've removed the drive shaft from the aircraft. So in that tail boom, there's no more rotating drive shafts. There's no bearings. There's no couplings. All of that's been removed. And we just have electric wires, copper running through the tail boom. In this particular case, for this vehicle, we did mount 2 generators, and they're driven off of what was formerly the tail rotor output drive shaft. So essentially, coming off of the main rotor gearbox on this aircraft, there's an output shaft that connects to the tail rotor drive shaft system that's now been removed. So we're instead taking that rotation and driving we added another gearbox to split it into 2, and we're driving the 2 generators off of that tail rotor drive shaft output. Those generators generate electricity that goes through a control system, which ultimately feeds through to the electric motors. And again, as I've described, so far to date, the commands are driven by the pilot's pedals. I think that's probably a good introduction. I think I'm going to emphasize again so everyone understands fixed pitch fans and constantly changing RPM. And I'm going to get into later why that's very important, and I'm emphasizing it because visually, a lot of folks, probably more so non-aerospace folks see this and they say, okay, interesting, 4 instead of 1. Why, what's the difference is, but I think what's behind the scenes that the technical folks really can appreciate is that there's much more differences than just the visual, which is that fixed pitch and variable RPM system. So with that, I'd like to, Jim, play that video, if that's possible. And I think I've been told that the sound isn't going to work, but that's okay. You can all, I would encourage you all, I tried it this morning to make sure if you go to Google and type Bell EDAT and go to videos, you can find this video quite easily. So you can watch it on your own afterwards as well. Very good. So I don't know if that was the same for everybody, but it seemed a little bit choppy. So I think I would definitely encourage folks to again go Google Bell EDAT and go click on the video link and go watch the aircraft flying. I think it's pretty interesting to watch that without the buffering. So Yeah, you'll notice, we've been pushing the envelope since first flight on this aircraft. We're doing sidewards flight towards the right, sidewards flight towards the left, reverse flights up and away, etc. And the aircrafts perform great. So we're continuing to develop it, but all in all, the flight test program has been going very, very well. So let me spend a little bit of time digging into the first benefit that I've got listed on the slide here and how that works. So reduced noise. Now, let me start with the main reason that noise is a benefit of this design, and that is the variable RPM blades. So what most folks probably don't know, except for some of the perhaps very, very astute, probably I'm sure in this VFS audience right now, but I'd say it's fairly unknown. What is the sizing condition or the flight condition that sizes the anti-torque? And for Bell aircraft, just due to the rotation of our main rotor, basically for us, it's right sideward flight. So when the helicopter is flying sideways, and you can see in that video, we've got a clip of it doing this. When it's flying sideways, up to 35 knots is the maximum design point that we designed to. I believe the certification requirement is actually 17 knots, but we designed beyond that. That is the maximum anti-torque thrust required, and that's because the anti-torque is having to stabilize the aircraft and counterbalance the main rotor torque, while additionally it's having to translate the aircraft, sideways. So that's the most thrust required out of the anti-torque is in that condition. What that means is that in every other flight condition, the anti-torque is over-designed, right? So when you're in a hover in zero wind, and I should specify, if you're in a hover with 35 knot sidewards wind, that would be the equivalent of flying sideways at 35 knots. So those would be the same. But if you're in a hover with zero wind, or if you're in forward flight, or if you're in any other flight regime maneuver, your anti-torque is not using full thrust. So what's unique about this system being RPM controlled and not variable pitch blade controlled is that our tip speeds, which is I think most people know, the most important driver for noise is tip speed of the blades. Our tip speeds are reduced, except for in 35 knot sideward flight. So in 35 knot sideward flight, EDAT will be at its loudest condition because it's be humming along at maximum RPM and all its tip speeds will be at max. But in every other flight condition, your tip speed is going to be reduced, even to the point where if you're in forward flight at a certain velocity, the aircraft actually gets yaw stability through the vertical fin, and essentially a tail rotor is putting out zero thrust, or zero thrust is required. And in our case, that means we can actually completely turn the fans off and they can be at 0 RPM and making no noise at all. So that's really a really important feature of this to get into the reasons for the noise benefit is the RPM. There are definitely other aspects of it. Of course, the shrouding is one aspect. Also, the fact that we have 4 versus 1 puts out a higher frequency noise. When you get into the details of acoustic analysis, you'll find that the higher frequency noise tends to attenuate faster, meaning that it gets quieter or doesn't travel as far a distance. So if you're standing, say, 500 feet from the aircraft, you're probably going to hear a lower frequency noise is going to travel further than a higher frequency noise. So there's some of that benefit. There's also development that we're still working with on different frequencies within the different fans. I won't go as far as to say that they'll cancel each other out, but you can imagine that we can play with the noise on the 4 different fans, and we can offset some of the noise frequencies, and we can play with some sort of form of noise cancellation or noise reductions with doing different RPMs and different noise frequencies. So that's the main benefits there for noise. Hopefully you guys, maybe I'll just get through the pitch real quick. It shouldn't be much longer, and then we'll go back and we'll open up for questions. So I guess write down your questions or make yourself a little note. The next one I have here is safety. So a couple things with safety. One, I'll start with, it is a fly-by-wire system in the full aspects of the mean. There's literally, like I said, copper wires driving back there. There are no mechanical components connecting the tail to the main. So it's definitely fly-by-wire, and what that offers is a lot of opportunity for reduced pilot workload. So the 525 is one example that Bell has that we're very excited to be getting very close to certification on that aircraft, and the pilot feedback has just been phenomenal with the fly-by-wire system. I mean, you can essentially get to the point where the aircraft flies itself, and it can do certain landings and procedures with very minimal pilot workload required. So that's one benefit there. Redundancy, of course, we all know about redundancy and FMEAs, failure modes and effects analysis. So one of the nice features about EDAT is that it can still has thrust output even if you lose 1, 2, or even 3 of the fans, right? So for instance, if you had a bird strike in there, or if you had some sort of mechanical failure due to whatever reason, you still have partial thrust capability. That's unique to any other system that's out there today, where if you caught a bird or had a failure in a tail rotor, now you've completely lost anti-torque capability. So this is an interesting feature. One interesting aspect of this that probably doesn't come to mind initially, but as we thought through it, could be another benefit is in aircraft readiness. So maybe more so for the military aircraft, but we all know that one of the biggest challenges with any fleet operator, or any operator for that matter, is making sure that you have all your parts, all your maintenance is done, and your aircraft's ready to go. So one unique feature about EDAT versus a conventional is, with a conventional tail rotor anyways, you need every single component in full working function to be able to take off. However, with an EDAT, theoretically, if you were missing, let's say, an entire electric motor back there, so you only had 3 electric motors, you could still fly this aircraft. You may have reduced mission capability. You might not be able to go 35 knots right sideward flight, but you could have reduced mission capability, right? You'd have to get into the details about payload and altitude and all those things, but there is opportunity there to provide operators with partial mission capability with EDAT, which is a unique ability to be able to swap components and to be able to keep your fleet ready, even despite having part shortages. So that's kind of it on redundancy. Just for note on this particular aircraft, so the design point for this was ability to hover with 0 wind with 2 of the fans completely inoperative. So basically what would happen there is, if you're hovering in without any wind, your RPM on all 4 fans is going to be whatever it is. Let's say it's 5,000 RPM, 4,500 RPM. If you lose 2 of those, the remaining 2 are going to kick up in RPM. So they're going to run at higher RPM to give you more thrust to counterbalance the dropping of half of your fans, and you should be able to hover with that. So and then you can get into even more even in emergency situations, if you only had 1 of your 4, you still do have some thrust to give the pilot some ability to help stabilize the aircraft as they get down safely. Finally, on the ground. So, again, one of the nice features about electrically driven fixed pitch variable RPM systems is, as soon as you have friction on the skids, you can turn off your motors completely, right? So that's much different than any conventional system now that has a mechanical drive shaft that's linked basically directly to the engine. So as soon as you even go to start up the aircraft and you're warming up your engine, your anti-torque and your main rotor are all spinning. In this case, they can be completely off. And then, of course, when you land and you have to do a shutdown, and you're waiting for your engine to cool down, you're just waiting for the inertia to slow things down. This one will be instantaneous. Like I said, as soon as you have friction under the skids, you don't need your anti-torque at all anymore, so you can turn it off. So that's very nice for certain missions like EMS, for sure, right? If you're landing on the side of a highway and you've got patients, you've got bystanders, you've got crew walking around, it's a stressful situation. It's nice to know that you don't have anything rotating back there in the way. And you also, it's nice to not have to shut down your engine. You know, a lot of operators, especially EMS, will tell you that the last thing you want to do is when you're on the side of a highway picking up a patient is shut down your engine, because, you know, engines, you always have that risk that they may not start up, or you may have an issue when you do a start stop. So being able to keep engines running consistently is certainly an advantage. It can actually help with DOC as well, to reduce the number of starts and stops on the engine. And that gets into my final point on the slide, which is DOC. So this is, you know, analogous to automobiles, where we all know the electric cars now are lower maintenance costs, right? It's pretty obvious when you have less moving mechanical components, you have less friction items, less lubrication and oil and all that. There's less maintenance, right? So you know, electric wires and, you know, generators and motors do require maintenance for sure, but in general, there's less wear and tear. You know, there's certainly no elastomeric bearings here on the rotors. There's no hanger bearings in the drive shafts. There's no couplings. You know, a lot of these items are just simply removed. So the electrical system is definitely going to offer reduced maintenance costs. So with that, that's it in a nutshell overview, and I'd love to open up the floor for questions and keep the conversation going.
Well, Eric, I must say that you have done a good job of stimulating the conversation here. We've got a lot of questions that have come in. So first, I want to just thank you. It was a great presentation. It was very informative, and I congratulate you on getting the thing up and flying. So it's a great accomplishment. So as we jump in, I'm just going to go through them in the order that they were received. I do see there's a couple of them that are redundant, so I'll try to combine them together as we go through. So the first question that comes from Tom Freud is, are the generators coupled to a battery pack? And if so, is motor power supplied via the battery pack?
Okay, so yeah, great question. And in this particular case, no. We kept it simple for this one. We do not. So the generators make electricity, and they go directly, the electricity is generated directly from the rotating gearbox, and we don't store the energy in a battery. However, it's very possible, it's really, you could swap the generators altogether for a battery. So this would work just the same as long as you're getting electric energy. And actually, maybe it reminds you of another point to add. Questions have come up in the past about, you know, what happens if you lose an engine? So if you're in a single engine aircraft and you know, your engine fails, right? So in this particular case, you would still have electricity because our generators are coming off of the gearbox. So as long as your main rotor is spinning, even if you're without an engine, you're generating electricity on those generators. But yeah, the short answer is no, we did not use batteries in this particular case, but you could.
All right. So kind of like a diesel locomotive in that respect.
Yes.
Okay, very good. So let's go to the next question. In terms of power to weight, how does the floor fans, controllers, wiring, and structure compare to the mechanical drive shaft and tail rotor?
So great question. With the weight, so we have not optimized this for weight at this point. You know, I think what's and I know I get this a lot of questions along these lines pretty frequently. You know, we've got an aircraft flying, so people often say, well, okay, when do I put my deposit down? When can I get this aircraft, right? So I always have to remind people that this is truly innovation here, right? So to be totally honest, we did not know 100% if fixed pitch rotating blades would even fly. Would it even be hoverable? Would you have enough responsiveness? Does this concept even work? So our main mission in this demonstrator aircraft was to just make sure that this concept of EDAT, electrically distributed anti-torque with fixed pitch blades, is actually flyable. Happy to say we've definitely achieved that. And now we're into the next phase, which is, okay, now can we get the weights optimized? Can we get, you know, the system, you know, down the path towards certification? So in this case, just to, and maybe to add to that, you know, we didn't want to wait around, right? So we didn't want to spend time optimizing, analyzing, spend years doing that and go fly something. We wanted to fly and figure out, is this concept even viable as quickly as possible? So to that point, we used off-the-shelf components, right? So we used motors, generators that we could get our hands on right away. So we haven't done a true comparison of a production, mechanically driven system versus a production electrically driven system. We just haven't done that yet.
All right, very good. All right, so moving on, and I think you did address this earlier. In fact, I'm pretty sure you did, but are the tail motors individually controlled? And that also comes from Tom Floyd. The previous question came from Bruce Tenney, by the way.
Okay, yeah, great question. And so basically, yes, they can be. So all 4 motors absolutely have independent controls that they can be. For simplicity, when we did this, we just kept them all basically going the same direction. Although I will say, as we were going through the flight development program, we did find a couple situations where we found it advantageous to actually offset 2 of the motors from the other 2. And one example of where this comes into play is when you get into the frequencies or the dynamic responses. So as you can imagine, we're swinging from positive 6,000, let's say, RPM to negative 6,000 RPM. You're going to hit a mode in there, right? So in certain cases, in order to not dwell in a natural frequency, what we would do is we would actually have 2 of the fans, jump ahead of that RPM and have the other 2 fans jump below that RPM. So the net thrust equaled as if you were sitting in that, all 4 fans at the same RPM thrust point. Does that make sense? So basically, it's kind of an interesting game you can play where you can, as long as your thrust is what you want, you can have 2 fans going negative RPM and 2 fans going positive RPM, and they could be at 0 RPM, net. So, or 0 thrust net. So anyway, so the answer to this question, yes, they can be independently controlled, but for the most part, at this point, like I said, first phase, we kept them all the same for the most part, but there's certainly opportunity to look at more opportunities there.
Great. That's I think that's an important characteristic, is to be able to individually control. That's one of the benefits of going to electric, right?
Yeah.
So the next question also comes from Bruce Tenney, and it's, are the electric fans more or less powerful than the tail rotor it replaced?
Yeah, so we designed this system to be the same thrust as the conventional system. So we designed to the same 35 knot right sideward flight thrust requirement that our conventional system is designed to. So yes, they meet the same maximum thrust as the conventional.
All right, great. It's a good starting point, right? So easy to compare data. Our next question comes from Tony Osborne, and he questions, how would you expect an optimized EDAT to look? Would you need to have fly-by-wire control systems to work in conjunction with the system to get the best use from it?
Great question. Well, you have my brain going a little bit there when you said how would you optimize EDAT? I have to, and I want to make sure this community understands that there's a lot of opportunity here. We're very excited that we've now proven that this concept works, but as far as optimization, there's a lot of work to be done. So I would really hope that universities and researchers and other folks will start diving into this. For example, when we initially decided how many fans do we want to use, right? We knew we wanted more than 1 because we wanted that redundancy. But do we want 2 fans? Do we want 20 fans? And you can look at all the different case studies. In our case, like I said, we made our decision mostly because of what motors we could find off the shelf and ready to go. But by all means, I'd encourage folks to consider maybe having 5 fans or 8 fans back there is optimal. So that's one note I'd like to put out to the community to hopefully stimulate some efforts there. To the specific question was, I think about flight controls in the fly-by-wire. Absolutely. So there's a lot of work that we still have yet to do with, in a perfect world, the pilot pulls collective and has his feet off the pedal, and the aircraft is stabilizing itself, right? I mean, we have that capability with the right flight control software and algorithms, but right now it's like I said, it's just the pedal is still controlling the aircraft, or sorry, the pilot is still controlling the aircraft through the pedals, but there's a lot of opportunity to do more sophisticated flight controls. Yeah. Hope that answered that.
Okay. This next question, I'm going to combine one from Mike Hirschberg as well as David Clooney. The first part is why 4 fans instead of 1, 2, or 3? And to follow on with that, with 4, why 4 rather than 1? Is the inertia of the larger blades too slow for response?
Yes, yeah. So great question, and that is true. Responsiveness is something that we do have to keep an eye on, and it's absolutely accurate that the larger, the less fans you have, the larger they have to be, and the more rotational inertia they have, and absolutely they're going to have more challenges with being responsive. So that is part of the equation, is balancing the responsiveness. But like I said, 4 is not a magic number. I would simply say I think you want at least 2, and the reason for that is because when you look at the reliabilities of electric motors and generators, right, they are not quite as reliable as a mechanically driven system. So you do have to account for that, right? We've got years and years and years of mechanically driven systems reliabilities, and they for the most part are quite reliable. Electric motors and generators I think still have some way to go, and I don't know if they'll ever quite get there. So having at least 2 gives you that ability to, if you do have a failure in the air, you still have some partial authority to get you down safely. So I think that's important. But then if it's 2, 3, 4, 10, 15, 20 fans, that really is just going to come down to weight cost assessments. And it's going to be a very complex optimization. So again, I'm really excited to, now that this is out there publicly, I'm really excited to see if some researchers out there can start looking at maybe there's a more optimal configuration than the 4 fans that we've put out there. Good question.
And that's a great segue to the next question from Tony Osborne. What is the plan for the modified aircraft? Will you keep flying it? Will you test some different EDAT optimized designs with it?
Yes. So obviously, we're not ready to announce all of our plans and what we're working exactly. Some of that's still behind the curtain, but absolutely, we're still flying the aircraft and we're still developing it. Right now, I think we can successfully say that we have proven the concept, it works, and now we're into the phase of optimization and we're fine tuning, the performance characteristics, pushing the envelope further, and really continuing to optimize the system. Absolutely.
All right, great. Look forward to seeing that progress.
Yep.
The next one comes from Tom Freud again. Do you see any reduction in the overall vibration of the tail?
Reduction in overall vibration. And I'm not the dynamicist expert here, so I don't. Somebody else could probably answer that more intimately, but at a high level, no, we didn't see any issues. I mean, we did have, we had instrumentation all over, the blades, the tail boom, the fuselage, everything. We did have our typical tweaks that we had to make due to dynamic loading and things like that. So we did make those tweaks where we needed. But all in all, we didn't see any fundamental or major issues with dynamics or vibrations of the tail boom or the system.
All right.
Okay. Yep.
And then how about the decibel reduction for the EDAT in comparison to the equivalent tail rotor?
Yeah, no, I know. Great question. I figured that was coming. As I've learned, I'm not an acoustics guy by trade, and I've, I start talking with those folks and pretty quickly it goes over my head, to be totally honest with you. It's not as simple as 1 decibel number. I think folks in acoustics will understand that there's in-plane acoustics, there's out-of-plane acoustics, there's flyover, takeoff, hover, all the above. But what we can definitively say is that we did see a significant reduction in decibel levels. You know, you see more, the most significant reduction is in the forward speed flyover. So, you know, folks will probably know that there's a couple different certification standards for acoustics. There's a flyover, and I don't want to get stuck quoting the wrong terminology, but I know that there's one method where you just do a flyover, and I think you have 3 microphones on that one. Then there's other ones where you're doing an approach, a takeoff, and maybe a flyover well, and you're taking an average of them, and that's how you get your decibel equivalent rating. So in this case, I would say for EDAT, you know, you're going to get the most bang for the buck with noise on the flyover. But it is, like I said, if you're not in 35 knot skyward flight, you're at reduced tip speeds. So you are going to see, you know, noise improvement across the board. Yeah, I'm dancing around a number. I can just tell you, you know, we've seen in the range of 6 to 7 dB, just to kind of throw a number out there. But like I said, it's much more complicated than just putting a single number on it. But we'd say it's significant.
Okay. Do you know if it's a different signature? It's a different frequency response that you see too?
It is definitely. It's a higher frequency. So it's really exciting to stand next to the aircraft and hear it. And we had a conventional 429 right next to the EDAT 429. You can hear them. You know, I think some of the words are, at least, you know, from a layman acoustics guy, the conventional 429 had more of a growl, kind of a low pitch, kind of growly noise from the tail rotor, and this one had, you know, a higher pitch, kind of a, you know, I don't know how to describe it, but a higher pitch kind of fan noise. So it's a different tone for sure. Yeah, but it's a higher pitch in general.
Okay. Yep, that's what I would have expected, and you confirmed that. So, yeah. Our next question comes again from Bruce. Do you control all 4 fans at the same RPM in a general mode of operation, or do you deliberately choose what RPM to use for each of the 4 TUs? And by what criteria do you choose the RPM for each fan?
Yeah, so you know, our initial going in position was all 4 fans are the same. It's, you know, I want to call it, it's a dumb system. And by that I mean, you know, pilot pedal position translate to an exact RPM on all 4 fans. So that's where we started initially, just to try to mimic a conventional system. As we did get into, you know, I mentioned a little bit as we got into details of, you know, maybe a dynamic mode, and we wanted to avoid dwelling there, we took 2 of the fans and bumped them up, you know, to kind of cross over that, and put 2 of them a little bit lower than that RPM, so that the net thrust was where we wanted it, but you weren't sitting in that mode. One other thing to kind of mention with that, you know, and this was some of the tweaks we discovered, is, you know, what's nice about the system is, and again, in kind of layman speak here, we'd have a lookup table, right? So you'd have a lookup table that had pedal position to output RPM. And what we did is we initially tried to match the conventional, based on flight data, the conventional system as close as possible. But we got pilot feedback that said, you know, hey, you know, it feels a little different here, you know, or a little different there. And we could go in there and very easily just update our lookup table. And, you know, the engineers, you know, smart folks were putting in different curves and different relationships between pedal position and RPM output to kind of tune it based on pilot feedback. And you can just upload that, you know, very easily. So that's also been kind of a nice feature about this, is you can have this sort of rapid cycle of tweaks. Whereas we all know with a conventional system, once you get a gear ratio identified and you've got a gearbox built, you know, that gear ratio isn't changing, right? So there's some opportunity there. Yeah.
Yep. Indeed. So this next question comes from Frederick Valeray. Eric, did reliability steer to have the 4 separate rotors, or from an integration standpoint, 3 would have been a better or balanced and integrated system? Was reliability kind of what drove you to the 4?
Yeah, no, great question. You know, I think I'll say there's a lot of work to be done with reliability. When you get into the details of a certification FMEA, right, a full-blown failure modes and effects analysis, you're going to look at all those probabilities and how they add up. Of course, more redundancy helps that score. But to answer the question, in fact, you can look at our system. I've already talked about, we have 2 generators, right? So if one of our generators fails, we actually lose 2 motors, right? So we've got the system that, and just we've got them diagonally positioned. So we looked at all that, right? So if you did lose one of our generators, you're going to have 2 diagonal motors come off, but you're still going to have half your thrust capability, which, like I said, if you're not trying to do a 35 knot right sour flight, you should have enough to get down safely. So that's the way it's designed.
Okay, it'll probably be something you look at as you progress through your different configurations and tests.
Yep.
So, once again, Bruce comes back on with, did you create a special cooling approach for the generators and the power control electronics?
Yeah, great question. And that's obviously a big part of it, is how do you cool these things? So what we did, again, and you'll understand what I mean by, we did this thing not optimized. So we actually took a 412 transmission sump system, because we had one, and we put that in the aircraft, and that's our oil cooling system for the generators. I mean, we literally just pulled parts that we could get to get this thing going. So in a production situation, I think you would certainly want to look at integrating the oil cooling with perhaps the main rotor gearbox, or maybe even the engine oil cooling system. Look for some optimization in that regards. And I'll be honest with you, we still have on the table, consideration for air cooled. I mean, air cooled has its advantages. You drop all of those liquid, cost complexities and maintenances. But of course, folks that are pretty familiar with air cooled versus liquid cooled, the power densities is also the challenge there. So that's just something to look at. All open trade space for sure. Yep. But to answer the question, we have an unoptimized 412 cooling system doing ours.
Fair enough. I understand what that means. Yep. All right. So coming back, Tony Osborne comes in with, can you clarify that you can still reach 35 knots sideways flight with the loss of 1 or 2 motors?
So no, we cannot. So good question. And the way that we're designed right now is your maximum 35 knot right sour flight condition is with all 4 fans operating. So if you do have 1 or more out of operation, then you would not be able to achieve that condition.
Okay. Okay. Julian Torres asked the question, is Bell targeting the EMS market for an initial launch? And if not, I'll add to that, is there a target initial launch market for the EDAT?
Yeah, so we're not ready to publicly comment on launch customers or anything like that, but I think it's fair to say that EMS is certainly one of the industries that's shown a lot of interest in this, especially with their missions and how they have to land and take off, and they've got a lot of hectic things going on around the aircraft in those situations. But certainly there's lots of industries. I mean, I'll even say, right, the whole air taxi industry, right? If you think about, folks that are going to be riding on this future state air taxi, where you're taking it for your daily commute to work, these are non-aerospace, non-helicopter people, right? So they're not going to necessarily be as educated about, safety when walking around a helicopter and all that. So I think there's certainly advantages with EDAT for that air taxi market, and then also, of course, the noise benefits. But there's a lot of industries that have some interest, and we'll kind of just see where it goes.
Okay. Yeah, I would think tourism would be interested too.
Yep, definitely.
All right. So Frederick comes back again with another question. What are the next steps envisioned by Bell? As apparently this development was made using commercial off-the-shelf equipment. We assume that you're going to optimize that, and so what are your next steps for the EDAT?
Yeah, so that's it. I mean, it's optimization. We wanted to first, like I said, prove the concept, because you don't want to go spend a whole lot of resources and time and energy figuring out this concept doesn't even work, or it's got some fundamental flaws. So we haven't hit that roadblock yet. In fact, we've we've gone pretty far with the envelope, so we're feeling very comfortable. And now we're just really looking at optimizing. For example, we have, we just have simple blades. We have simple airframe structure. I mean, this is, you can imagine it was done quickly. So there's lots of optimization opportunities, we'll say. Yeah. Well, one thing I'll add to that is, and again, this is really sort of a plea, if you will, for the community, is, the modularity of this system is very unique. Whereas, I'll say it's as simply as we can kind of plug and play different systems on the back of this thing, right? We've already crossed the bridge of taking a mechanically driven helicopter model and put this EDAT on there. But now, if let's say a university or someone says, you know what, I've come up with a 7-fan system that has, whatever optimization on it, and we've done all this analysis, well, we can pretty easily unplug those wires and plug in the new wires and go put that on there, right? So there's a lot of opportunity to do upgrades and quick, rapid testing of different optimized systems. Whereas on a conventional system, like I mentioned, once you've got a gearbox designed, built, you're not going to change that gear ratio. Even the drive shaft angles and the couplings have all been designed. You're not going to, raise that tail boom up a little bit, or you're not going to, do this. But with an electrically driven system, you just got wires. You just got to bend the wires and plug them in. There's a lot of opportunity for quick upgrades. So
yeah,
looking forward to seeing what folks come up with. Yeah.
And even some additional configurations you could put on pusher props too.
Absolutely.
Of sorts. Yep. So yeah, lots of unique things you can do with electrically driven.
Yep.
Even though Mike Hirschberg has left, he did leave. He did ask a question before he left, and the photos and video that were provided for the promotional piece was from last winter. Can you elaborate on what's happened since then, and are there plans for operational service? I think you kind of covered that last part.
Yeah, so the aircraft, is still flying. We've flown it recently, and in fact, we've been planning a media day since about the springtime, and we all know the reasons why that's gotten pushed and everything. But fingers crossed, I think we still do have another public flight planned for before the end of the year. So we'll be able to show some more videos, and if that all goes well. But it's a constantly changing environment, and that's the main reason I'm going to use the COVID excuse as to why we've had a little bit of a disruption. But in the meantime, the team has been consistently working on even if they're not flying the aircraft, consistently work on analysis and basically analyzing the data, right? So we have a slew of flight test data that we're now crunching through and looking at, what is the next steps. So, and you guys will be able to see it flying again here, I'm hoping before the end of the year.
Great. Yeah. When you do have those media days, obviously we'd be interested in participating in that if we're allowed to. So.
Yep.
See, next question comes from Pierre Richard. What percentage of the main engine power is used to power the EDAT?
Good question. I don't know off the top of my head, so I don't want to get caught lying. What I can kind of, to answer that question, I can say that it was pretty close to the same as a conventional system. I want to say it was like 2% more power or something like that, but I really haven't looked at those numbers in long enough, and I'm not the right guy to answer that, but I will say that it was pretty close to conventional system. There's downsides, of course. Mechanical systems are quite efficient. Electrical systems, have some efficiency challenges, so there's certainly some power loss there. But some of the benefits that we're taking advantage of our ducted system, right? So when you've got a duct effect, you do get some advantages there. Also, what's kind of interesting is if you look at a conventional 429 anyways, you've got a big vertical fin impeding, a decent amount of the rotor area or the tail rotor area. So in our case for the EDAT, right, we don't have that restriction anymore. So there's some things working in our favor there, but I think all in all, short answer is it was pretty close, and maybe it was nominally required a little bit more power than a conventional. And again, you know, I'll say that's with, you know, blades that we just put out there with, you know, without really looking at optimization, you know, like the duct or the gap between the duct and the blade, right? So that's something that, you know, we wanted to just make sure this thing was safe and we weren't going to have contact with rotor and stator there. So we kind of kept a nice conservative tip gap between the duct and the blades. But those are all things that as you got into it, you know, you could certainly optimize, reduce your gaps there and get some more power and efficiency. So a lot more to go there, but yeah. Good question.
Yeah. Speaking of the blades, how many blades are on each fan, and what is the approximate solidity?
Oh yeah, good question. I don't know the solidity, but what I do know is that we designed our hub, again, you know, of the tune of what we built here. We designed it to be modular. So we designed it where you could have up to 8 blades per fan, but you can also remove blades and you can run less. You could run 2 blades if you wanted. So we flew with 8 blades per fan. So 32 total, and then we've also flown in our latest configuration, in fact, is 4 blades per fan, so 16 total blades. So yeah. Okay.
Are you able to share what brand of electric motors you used?
Absolutely, yeah, we're happy to share. Safran has been working with us and a great partner on the motors and the generators, in fact.
Yep. Great. Thanks to Safran. Frederic comes back again and asks the question, identical fixed pitch on each of the 4 rotor and fans, or having 4 different settings to play with in controlling the 4 motors speed and thrust independently?
Great question. So we did design our hub to be able to change the pitch of the blades on the ground, right? So the mechanic can go put in a 2 degree or 4 degree or 6 degree blade pitch, but then once it's locked in, you go fly with that. So you're right that you know, as we got into the optimization, we could tune this thing and have one of the fans at 6 degrees pitch and the other fans at 2 degrees. We could do all that. Again, not dynamic, right? We're not changing pitch in flight or anything like that, but you can do that on the ground. To date, we have done a couple different pitch settings for all the fans together. We have not yet experimented with different pitch, you know, for different fans, and you know, but that's certainly something that we can look into down the road.
And that's something you could use to, if you wanted to, maybe tune the audible noise too as well.
Yep, exactly. Great point. Yep.
Okay, our next question comes from Daniel Spira. What fan blade design compromises did you face to obtain sufficient aerodynamic performance for both positive and negative fan rotation?
Great question. You know, this is one where I think we were all a little bit surprised with how well the blades performed in the reverse rotation direction. So you're right that you know, you kind of optimize a rotor for spinning one direction. When you go in the reverse direction, your trailing edge is now your leading edge, and you know, there's some efficiencies reductions there. But in our case, we were actually very surprised with how efficient the fans ran in reverse. I don't remember the exact numbers, but it was certainly more than enough for what we needed. And you know, it must have some, I'm not the detailed guy here, but it must have something to do with the smaller, you know, airfoil and the smaller blades, you know, are a little bit maybe more tolerant of running in reverse than maybe a larger, like a main rotor blade, for instance, maybe. I don't know, but we did find that we had more than enough thrust in the reverse direction with running them backwards.
That's great. Yeah, that's a pleasant surprise.
Yeah.
All right, so we're coming to towards the end here of the session, as well as the number of questions we have left. So I'll plow on through it. I think there's about 3 left. So Any idea on the timeline to production, and will there be a price consequence to converting to an EDAT?
Yeah, not ready to give a timeline yet, nor price. Yeah, so it's a little bit early for that. You know, we're working it, and but no, we don't have any timelines yet. So.
Okay. And then the follow-up question is do you see EDAT fully replacing the mechanical tail rotor for future designs? And that question comes from Johan van den Busch.
You know, that's a really good question, and I think yes. I think EDAT does have the potential to be, you know, the best system for all anti-torque control in the future. It has the potential. I mean, we talked about the benefits, right? That a conventional system just doesn't have innately. We've got to get to the point where we've got to get an optimized solution out there, and you know, and just let the metrics and the numbers drive that. But I think a lot of the benefits with noise, with DOC, you know, safety, I think it has potential to potentially replace it. I'm not going to be as bold to say it is. You know, we still have to prove that, but I think there's potential.
Great. All right, saved the best for last, I think, or maybe the most interesting one for last. So
okay.
Tony Osborne comes in and asks, competitors have explored transforming existing shaft-propelled anti-torque systems to electric power. Did you look at that first and then discount it? Could you describe the steps you took to get to EDAT, the EDAT configuration you have now, and are there any benefits to electrifying traditional tail rotor systems?
Okay, I think if I'm understanding right, and Jim, help me out, the question is about taking a conventional tail rotor and putting an electric motor on it today.
That's how I understand it as well, yeah.
Yeah, so we did consider that, and you know, we're well aware that there's examples of those types of systems that have already been developed out there. To be honest with you, we quickly, the reason we came up to EDAT honestly was we were trying to make a step function change in noise, right? So we said, you know, we can go tweak blade tips, we can do a ducted system, you know, all this is stuff, and we kind of considered those incremental changes and still good. But we said, how do we change the game, right? We saw the air taxi market coming. We seen even the EMS operators with their hospital districts and noise requirements or constraints, and you know, just we really saw noise as becoming an emerging important parameter, and that's how we came up to the idea. We scratched our heads and said, how do we change the game there? And it came down to tip speed. We said, look, you know, tip speed is the main driver. So how do we how do we kind of fix that? And that's how we came to this idea, kind of essentially. You know, probably the other issue I'd say with that particular question is you've got to look at the redundancy. So if you've got a single motor driving a single system, you've got to look at, you know, that motor has to be reliable enough to be able to get down safely. So you may have to have two motors, you know, driving that one fan or one rotor system, or you've just got to have triple redundancy, or, you know, that's probably the other reason that we ended up where we did when we looked at the reliability of the motors and the electrical systems. We knew that we wanted to have multiple ones to give us that redundancy. That's probably I'd answer that, but that was a good question.
Yeah, and then Tony did come back and confirm that's what he was trying to ask.
Perfect.
So as it turns out, we are at the top of the hour, and we have come to the end of the questions at this point in time. So I want to say thank you for spending your morning with us and talking about the EDAT. Very exciting configuration, a great, as you say, step change in helicopter design going forward. And we look forward to following those great advancements and you keeping us updated on what you learn along the way, at least what you can share along the way. Yep. and again, I appreciate you guys. And this is a kind of a fallout from, or follow-up from some things from Forum 76. We appreciate your support from Forum 76 and your continued support of BFS along the way. So thank you again. I'll give a quick thank you to everyone in the audience for calling in today and listening, and for asking some really great questions. Yep. And then finally, I'll give a shout out to to our helper who makes these things run smoothly, and that's Chris Thompson, who's hiding out in the background, learning as much as he can. So with that, Eric, I'll say great work, and look forward to seeing you again. And thanks to everyone for dialing in, and we'll say goodbye for now.
Thank you.
All
Thank
right.
you.
Thank you all.